In this video I'm going to construct a peak model for doublet signal. The reason that we see doublet signal in XPS is related to the photoionization process. We start off with an initial state. This is the initial state of the electron configuration within an atom. And then a photon arrives and ejects an electron, and this produces a photoelectron that we might describe in this example as a 2p3/2 electron. There's another path by which the photon could be absorbed based on a p orbital, and that is an electron that has 2p1/2 symmetry. When it is ejected, we produce a different final state, and these two final states have different energies, so we see a split in the signal. And that's what we observe in practice. We see in the argon 2p spectrum a split in energy that is characteristic of an argon 2p photoionization. Now in general though, the ratio of the peaks that we see in a doublet is dependent on the orbital, and in this case the p orbital. We can arrange the electrons and their energies that are equivalent in two ways for p orbitals. We have 4 electrons that are associated with the quantum numbers 2p3/2, and we have 2 that are associated with the quantum number 2p1/2. This indicates that when we have photoionization of electrons with 2p3/2, it should be twice the number as we obtain for 2p1/2. And hence when we look at the argon peak, we can see a pair of peaks that are in a ratio that's close to 2:1. So this is the first indication that we are looking at doublet peaks rather than some type of chemical shift that might indicate different oxidation states of a material. We are genuinely looking at shifts that are associated with the physics of the photoionization process. And this is important for peak fitting because we can use this to construct constraints that help guide the peak model to a more reasonable solution than if we don't use any constraints at all. I will now construct a peak model based on observation of what I can see in the data based on one spectrum. I'll bring up the quantification parameters dialog window, and this provides options for creating a background and also component peaks based on synthetic line shapes. So first of all, I'm going to create a background, and the background is, in this instance, a linear background. I'm going to change that to be a Shirley background. So now I have a Shirley background, which is a very common background used in data such as these. I would like to also change the number of data points that are used to calculate the endpoints of the background. So if I change the average width to 10, then these vertical lines indicate the range of data bins that are used to calculate the point at which the background meets the data. So this is the start and this is the end, and pretty much the use of 10 data points, provided it doesn't cause the range of signal to go into the peak in some way or some sort of structure, that 10 data points either side of the datum that would otherwise be used to calculate the background, that gives a reasonably stable background calculated across data such as these. So once we've produced a background that represents the inelastically scattered signal, that is to say signal that would have been photoelectrons but for the fact that they were scattered within the material en route to the detectors, the scattering causes them to lose energy, and so they appear as this background. But what we're interested in a peak model is the photoelectron signal that has not lost any energy en route to the detectors. Creating a peak model involves constructing a set of component peaks. So I could create one and then make some adjustment using the mouse, and I'm holding the shift key down to adjust the width without causing the height of the peak to change, that has allowed me to position one of these peaks in this spectrum. So adding another peak, well, it has been positioned where the residual is the greatest, so I'm going to move that on the basis of my previous discussion that I need to have peaks appearing in pairs that have a given relationship in intensity. So I'd like to now impose the relationship that this is a doublet peak from a p orbital by ensuring that the area between these two components are in the ratio 2:1. So now that I've created a doublet pair, I can create another doublet pair easily by copying these. So I've selected the component that is controlling the area in the sense that B, this green one, is half the area of A. So the constraint A star 0.5 is forcing that relationship, and so I describe the component parameters in A as being the controlling parameters for this particular constraint. So if I press the copy button, this and also any components that are linked through constraints to this particular component will be copied and can be pasted into the data. So now I've got here a red one, that's my original one, and a blue one, both identically positioned with the same parameters. If I want to move the blue one, I hold the control key down, and that will cause me to pick up the later ones in the list that we see on the components property page as the component I'm interested in. If I don't have the control key down, then I would pick up A. So I'm holding the control key down so I can pick up C, and if I just drop the intensity of C, I get to see what D looks like too. So I can now move D and I can move C, and I end up with 4 peaks that seem to represent the data that we see here. Now, having placed a constraint on the area, the next maneuver would be to fit these peaks to the data. So let's see how well that fit worked. Well, we've got something that is somewhat consistent with pulse counted data. It's about unity for the residual standard deviation. The residual itself is reasonably good. There's a bit of an anomaly here in terms of the relationship between the envelope and the data itself. The envelope meaning the sum of all the component peaks, that must model the data, and if there's a disparity between these two, then we see it in the residual, and that's what this dip here and this rise is. There's something not quite right here. So that might make me believe that I need to adjust my line shapes. And I perhaps take LA60 rather than LA20. LA20 is closer to a Gaussian, LA60 is closer to a Lorentzian. So let's try that in all of these peaks, and I can input the equal sign anywhere in the string and press return, and that will cause the line shape that I've entered to be transferred to all other line shapes in this list of components in the peak model. I get a dialog window saying exactly that update line shapes in all components, yes, and you can see there's been a change, and even without fitting, the residual is now better in terms of a residual standard deviation. When I say fit, then I have certainly got a residual that suggests that this is a good approximation to data. The question still remains whether this is actually a physically meaningful peak model. Now, if I choose to look at the data set itself, it's apparent that these data have been measured multiple times. So let me scan through this list and observe the different spectra, and we see very similar spectra throughout this list. So one test I might do is to propagate the peak model. So this is going to propagate regions, components, and auto fit, and I press OK, and then each one of these spectra that are selected in the right hand side will now have this peak model applied to it and then fitted, so that we end up with other examples of how well this peak model is fitting data from Ar2p that is evolving, and not dramatically, but there is some evolution in these data. And the reason that's evolving is that the sample is changing with time. That what we have is an aluminium metal that is sputtered clean with argon and then is allowed to re-oxidize over time throughout this measurement sequence. So there is some sort of alteration here. You can see the relative area of these two components in the 2p3 halves is different. So we might think to ourselves that yes, we have a peak model that fits all of these data and we can characterize the changes through this peak model. However, it is possible that other changes are occurring in the course of this measurement. We are observing, for example, in the aluminium, changes that reflect the oxidation, changes in the relative intensities, and also the bulk and the surface plasmons. There's something happening, as we see in terms of these colours, over the course of the measurement. So we might expect to see changes also happening in the Ar2p. So let's take the Ar2p into a new experiment frame so that we can isolate the signal using the process data only. The only processing is the peak model, so when I tick the process data only, it will forget the peak model and we will end up with the data as it was originally. And I'd like to use this now to try and understand if there are any other trends that I'm not really spotting with the peak model. And I can do this using PCA. So if I overlay these data, and let's just make some adjustments, turn off the residual, and I will change from 4 the line width that data is plotted to 1. That speeds up the refresh rate and I can see the data now in terms of colors quite easily. Let's do a PCA. The PCA is going to transform the spectra that we see here into mathematical forms. These mathematical forms will be related to the data in the sense that the first one has a relationship to the average spectrum, and then the second form that I will create by PCA will tell me how all the other data deviate from the average. It's not really an average, it's a different type of average spectrum, and that will give us an indication if there is actually genuinely 1, 2, 3 or however many changes that are occurring within the data that can be recognized through the principal component analysis calculation. So let me do the decomposition. Press the PCA button on this toolbar and we do indeed see spectra. The first one looks very much like the spectra. It's actually very close to the average spectrum in its variations. The second one, now this is interesting because it's showing us that there are shapes. They are not physically meaningful shapes, but they show that there are deviations from that average spectrum that we need to investigate. If we go to the next PCA abstract factor, well, that's very much looking like the residual, in other words, noise. So on that basis, I believe that there are two abstract factors, the average spectrum and the deviation from the average spectrum, that we can use to reproduce all the data, and in doing so we can remove some of the noise. So I've overlaid all of these spectra. I can return them to their normal state. You see the noise when we use two abstract factors. So we're predicting using two abstract factors. We end up with data that no longer has the same level of noise. And the reason that I'm interested in removing the noise is that I now want to look at the difference between the first and the last in the sequence, and that will give me some idea of what kind of shapes are within these data that might have spectral significance. I'll take a copy, and using copy VAMAS block to new column, this will automatically copy processed data. These are processed now. They've been processed by the PCA prediction step. So when I copy, I will get a new column, and the new column contains the processed data. The old column still is processed, but it has a processing history that I can remove, and this is the PCA eigenanalysis. If I undo all of these, then we see raw data, and we see in the next column the processed data. So I'm interested in how the spectral forms change over the course of this experiment. And I can do this by looking at different spectra. If I have all of these data overlaid, I'm going to take the first and the last in the list of these data and subtract one from the other when I apply this button diff. So I press the toolbar button and it creates a new experiment frame. The list will contain the first one with experimental variable 0. That is the original spectrum at the top of the previous list, and at the bottom this is the original spectrum at the bottom of that list, and in between are different spectra that show how, if you subtract one of those spectra from the other, the spectral shapes change. So rather than trying to pick from this overlay, I'm going to scan through the list. So I'm using the arrow keys and I'm going down this list, looking at the data and trying to assess, on the basis of what I see here, what looks like the best form for the peaks in terms of what I recognize as XPS data. And as I keep going, I find the relative proportion of these peaks changes. And that's interesting, that one is preferentially removed relative to the other. And then I start to see something that doesn't make any sense. So I'm going to go back up and generally look at the shapes of peaks, because I expect them to be Gaussian-Lorentzian type peaks. So I'm willing to accept that the spectrum that I'm looking at now, and it will be highlighted somewhere in this list, there it is, I can take a copy of that, take the copy to the next column over, and let's see that it's there. Yes, that's the copy. I use the arrow key, move across, and then I can go down the list once again and look for the alternative different spectrum. So the idea is to pick two spectra from this list that represent the more significant changes in the data that we don't really see in the original spectra. So here's an example. This is looking quite interesting. That we've got now doublets in this Ar2p that have a different proportion from the first one that I selected, this one here. So let me copy that one to a new column. This is more bookkeeping than anything else. I'm simply wanting to have access to selection of the two VAMAS blocks that I thought were interesting. And now this is telling me that there is the possibility that we do not just have two peaks, that we have more than two peaks. And the reason that I think there are more than two peaks is because I see an offset here. And that offset suggests that I would be able to construct a peak model probably with 3 doublet peaks, and that would fit the data equally as well as the peak model that I've already constructed. But that wouldn't be enough to tell me that I should do that. This could be a mathematical artifact, so I need to look at the data and try and understand what I'm seeing. And this involves understanding how XPS works. And this is really quite an important point, is that XPS contains a wealth of information, and that information is often lost by noise or just making some basic assumptions about the peak model. Now, having analysed these data in this particular way, I've got a structure here that is in the background that to me is significant. And the reason this is significant is because I anticipate that this could be a surface plasmon that is being generated by virtue of the fact that the argon is implanted in aluminium. And this other doublet pair, well, the surface plasmon is not in the same position. In fact, it looks relatively flat. So while this is not definitive evidence that we have additional peaks, it's suggesting that we need to think about it rather than just assume that we had two sets of doublet peaks that would fit the data, so everything was just fine. Here we have something that I can relate to the physics of what I expect electrons to do when they leave an aluminium metal sample. So I anticipate that this one would be representative of a signal close to the start of the experiment, and this one might be representative of signal towards the end of the experiment, because at the beginning of the experiment we had aluminium metal. It then was oxidizing and something changed. So I can now test that hypothesis by copying these two peaks into my data set. So these are my component spectra. This is my data set. If I select the raw data, I can then perform a linear analysis of these data based on these spectral forms that I've got here, and I can do that using the toolbar button LA. And this creates a new data file in which the original data is copied in, a column representing the least square solution, which is the sum of these two other columns that have been scaled in a way to allow the least squares solution to fit the data in each one of these rows. So when I overlay a row, we see a fit of the spectral shapes that I've calculated to the data. And we can see one spectrum representing the metal, because I believe this is a surface plasmon that is very obvious in the metal of aluminium. And when I go down this list, I do see a change, that as I go down the list I witness the surface plasmon and the signal from the argon that is associated with the surface plasmon diminishing, and signal that is different from the metallic form. In other words, where the oxide is forming, I'm getting a different set of peaks in different positions from the Ar2p. And I go to the end of this experiment, and we can certainly see there's been quite a change in the response, certainly in the background, that is causing the fit to favour one of these shapes relative to the other. Now, I'm not saying that this is providing a solution and offering exactly the number of components to this fit of the Ar2p, but this is providing a wealth of information about what might be happening that is related to my understanding of the sample and my thoughts about how argon is being implanted in the sample by the sputtering process that cleaned the aluminium sample in the first place. So rather than immediately going for the obvious peak model, which was two pairs of doublets, I would think that it's more than possible that we have 3 or maybe 4 doublet peaks that we could use to analyze the data.